Hi everyone, my name is Miss Click-Para. I am an AP Biology and Chemistry teacher at Bayport Blue Point High School. Good morning. Hopefully everyone is up and watching live. If not, remember that you can go back and you can watch any of these videos all day. Since I'm the first one this morning, I just want to explain basically what's going to be going on. You should have had the screen to get to my link. There are 12 different topics throughout the day today. 12 different science teachers or chem teachers throughout the state are going to be presenting on 12 different topics. And all of those videos are going to be available real time, so you can log on at the time that they're supposed to be broadcasting. You can ask questions. The chat feature is available, so you can go on and you can chat with us. Or you could watch it later, or if you want to go back and watch them again, they're going to be available for you as well, so you can go to those links. So today's morning topic, nice and bright and early in the morning, is going to be reactions and equations. So without further ado, let's get started. Okay, so reactions and equations, there is a lot in this topic, and depending on which chemistry teacher you talk to, depends on what they're talking about when they talk about reactions and equations. So I'm kind of going to go over an overview of two different ways of thinking about it. You can think about it as types of reactions, balancing reactions, but you can also think about it as like stoichiometry and moles and things like that. So I'll kind of be covering both of those this morning. So let's start with the types of reactions. Surprisingly enough, there is about 15 to 20 different types of reactions you learn this year. It doesn't seem all that overwhelming at the time because we broke them into nice little topics for you. But there is a lot of different types of reactions. So there's chemical reactions. We have 4 different types of chemical reactions, and then we also have organic reactions. There's a lot of different types of organic reactions. And then we also have nuclear reactions. And then there's also redox reactions, neutralization reactions, endothermic and exothermic reactions. So there's a whole bunch of these different types of reactions. We're going to touch on a couple of these, and I know in your other review sessions today, you're going to touch on a lot more of them as well. Okay, and try something really quick. Sorry, it's my my first time doing one of these live streams, so I just want to make sure that you're seeing what I'm seeing. You are not seeing what I'm seeing. Interesting. Okay, so what can you tell me about this reaction here? So take a second and think about it. What can you tell about this reaction if you just looked at it? There's a couple different things you'd be able to tell. Okay, so when I'm looking at this reaction, I can tell 2 different things. One, I'm starting with a couple magnesiums. That's a type of element. And we have N2, which is a diatomic element. Remember, your Brinkelhoffs are all your diatomics. So Br2, I2, N2, Cl2, H2, O2, and F2. Now they're reacting with one another. There's some kind of effective collision going on between them, and then they're making this more complex compound. So what type of reaction is this? Well, this is going to be a synthesis reaction. So as we go through and look at this, we can also ask what happened to the entropy in this type of reaction. So think about it, ponder it. Okay, so in your brain, you should be saying entropy. Well, that's randomness. So we're looking at that, and we should see that we are getting less random. So we're decreasing entropy as we go. I'm going to try one more thing, see if you can see it the way I'm seeing it. Okay, let's try this. Worked last night. Let's see. That should work. All right, perfect. Now we're on the right track. Okay, so going back to that type of reaction. Okay, so when we're looking at this as synthesis, we decreased entropy. We made it less random. So we started with a bunch of different parts, and now we put them together into one more cohesive compound. Okay, so there's the first two types of chemical reactions are synthesis reactions. That's where you're going to take two simple substances and you're going to combine them. A lot of times you'll see two different elements being combined into one compound. Remember, synthesis reactions, we're decreasing entropy because we're making them less random. We're making them more structured. The other type, kind of the opposite of synthesis reactions, are decomposition reactions. So these are when you break down a compound into simpler components as well. So this would be an example of a decomposition reaction. So ponder for a second, what is happening to entropy in this reaction? So I see a couple of you are chatting live, so you feel free to answer the questions, my hypothetical pondering type questions if you want. This is a decomposition reaction, and we are actually increasing entropy here. And you can tell that in two different ways. One, we're taking this complex compound, we're breaking it into individual components, but we're also taking a solid and we're making it into a gas. So in two different ways, we're increasing entropy. Okay, so now take a look at this reaction. There's two different reactions here. See if you can place what types of reactions we're talking about here. These are both types of chemical reactions as well. All right, so we're looking at this. We see A and B as a compound and C kind of on its own, and then it's switching spots. A is coming out to be by itself, and then we have B and C as a compound. Down here, we have one pair, A and B, and C and D, and then they're switching partners and becoming A and C, B and D. So if you answered that the first one was a single replacement reaction, you are correct. And the second one would be a double replacement reaction. So let's look at single replacement reactions for a second. I forgot to mention, you should have your reference table out close to you, as well as a calculator, maybe some paper to do some calculations, and you should have your trusty calculator as well. So if you don't have those things, you may want to see, we are going to take a stretch break in a little while and go and get those things. Okay, so single replacement reactions. In my classroom, I like to talk about dating or dancing. So if we look at this funny cartoons, it seems like a stupid way to think about it, but it actually does work. And I know a lot of you have a lot of experience with this. So if we have a couple, let's say that they're dancing at in a club or whatever. So they're dancing, and then another guy comes over who's a better dancer. He is going to replace the not so good dancer and become part of the couple. And then unfortunately, this other one is going to be kicked out on his own. You can also think about this as dating. The more active male will get the female, and then the least active male will end away. So if we take this into more chemical land, we look at this reaction down here. We have zinc reacting with copper 2 chloride, and then we're creating a new compound and a new single element. Now, why does this happen? Why is this reaction able to happen? So ponder it for a second. Very similar to the dating situation, zinc is a more active metal than copper, and we can tell that by looking at table J. So if we look over here, we have copper down here, which is is on the lower end for the active metals, and then we have zinc all the way up here. Where is it? Up here. So zinc is more active than copper. So when they come in contact with one another, zinc is going to replace copper in the compound. Copper ends up on its own, and we end up with a new compound, zinc 2 chloride. Now, you may be sitting and being like, zinc 2 chloride, why the 2? So as a quick review, I'll poll the audience. Does anyone know why it's zinc 2 chloride and not just zinc chloride? Everyone's quiet now. All right, I'll help you out with it. Zinc 2 chloride, because zinc is a transition metal, and you need, if it has multiple oxidation numbers, then you need the Roman numeral in order to tell which one it is. Good job. You guys got it right. All right, moving on. So I want you to try to practice these. We're going to go through them one at a time. So you should have your reference table out. If not, I put a little handy dandy reference table, table J over here. So I want you to predict if the reaction is going to occur. And if it is going to occur, what are the products going to be? So you can either answer in the chat feature, or you can also just ponder and think about it. So the first one is going to be calcium reacting with lead 2 chloride. Okay, so yeah, Jake, you are right. This reaction is going to happen. And our products are going to be lead on its own with calcium chloride. Now, why does this reaction happen? If you didn't get it right, well, let's look at the table J. We know that our single one needs to be more reactive than the one in the compound. So if we look down here, we have calcium, which is right here. And we have lead down here. So calcium is significantly more reactive, so it's going to replace. All right, let's try another one. So we have fluorine, diatomic fluorine, reacting with magnesium chloride. Is this going to happen? Okay, there's a trick to this one. Now, instead of using the metal side of the table, we're going to use the non-metal side of the table. Same rules apply. The single one has to be more active than the one in the compound. So you guys are correct. This one is going to form products. We're going to end up with chlorine on its own and magnesium fluoride as the compound. All right, last one. Try this one. Okay, great job. This one is actually not going to react because PB is not more reactive than Na, so we're going to have no reaction here. So if you were to put these two compounds together, or this element with this compound, nothing would happen. You would just see the same things that you put together. All right, so let's move on to double replacement reactions. I really liked this little cartoon that I had found. Remember, we're going to have, they're always found with ionic compounds. So you're going to have a cation and an anion. Cation is your positive ion, your anion is your negative ion. And then they're basically going to swap partners. So they're going to start with one pair, and then the cation is going to pair with the opposite anion, and they're going to work from there. So now you want to be able to recognize these double replacement reactions. You want to be able to look at it and be like, oh, yep, definitely double replacement. K was over here with Br, now K is over here with NO3. But you also want to be able to predict if the products are going to be soluble or not. A very common question in a double replacement, especially in a part 2, would be to look and see if the compounds produced are insoluble or not. So I'll give you a moment. Take a look at this question. It says, determine the insoluble compound produced by the following reaction. Okay, so take a moment. I put reference table F up here as well. Remember, table F is really good for predicting insoluble and soluble compounds. Okay, so now looking at this table, just a really quick overview on how to use table F. You have to be really careful reading it. In this column, you're going to have soluble compounds, making the exceptions insoluble. However, on the other side, these are all listed insoluble compounds. So if these ions or polyatomic ions are in the compound, then it's going to be insoluble unless they're combined with something in the exception. So on this side, the exceptions are soluble. On this side, the exceptions are insoluble. So it says which of the products is insoluble. So first we'll look up KNO3. So you look up, you can look up either K or NO3. K is not actually on this, so we're going to look up NO3. So we see NO3 is right here. NO3 is usually soluble, and it has no exceptions, making this compound always soluble. So that can't be our answer. So then we go to the next one, AgBr. So we look over, here's Br. Usually it's easier to search for the negative ion. So Br is here. Br is normally soluble. However, when it's combined with Ag, Pb, or Hg, it's going to make it insoluble. And in this compound, we have Ag with it. So this is actually going to be insoluble. So if you said AgBr, you were correct. All right, so now moving on to organic reactions. I know for my students, these were a little wishy-washy. There's a lot of them. You do have another review session on organic later, but since this is types of reactions, I just wanted to give you a moment to ponder some of these types of reactions. So we're going to put one up at a time and see if you could identify what type of reaction we're looking at here. So the first one, we have methane reacting with O2, giving CO2 and water. Oh, so I see a couple of you asking questions on the last one, that it says Ag plus in here. If we figured out the oxidation states on this compound, Br would be a -1, Ag would be +1. So this says Ag plus here because in this compound, when it's combined with Br, it actually is Ag plus. So it's not Ag, it's not an atom, it's an ion because it's forming an ionic bond here. So that's why it's Ag plus here. Hopefully that that helps out. Okay, so a few of you guessed at an addition reaction. So this down here is an addition reaction. What about this one up here? What are we thinking for this one? For number one. Okay, if you said that this number one was combustion, you are right that the bottom one is addition. It came up in the wrong order. But this is combustion. Combustion reactions are always going to have CO2 and water as their only two products. So you're never going to have anything else. It's always going to be some type of organic compound with carbons and hydrogens reacting with oxygen. So they can change what compound this is, but your products will never change. It will always be CO2 and water. All right, try this next one. What kind of organic reaction is this? Good job, Jake. This is fermentation. And how do we know that it's fermentation? You're going to take, you might even remember this from bio. We talked about it with ethanol fermentation or alcohol fermentation. You take a organic compound, usually a sugar, and you're going to break it down. Your two products are always going to be an alcohol and carbon dioxide. So how would you identify this as an alcohol? Because of this OH functional group hanging off here. Okay, this next one, a little bit trickier. So we have an alcohol reacting with an organic acid. So what are we thinking on this one? Good job. This one is esterification. And how would you identify this as esterification? Okay, esterification is going to always be reacting a alcohol, which remember we have the hydroxide here, so you're going to have the OH group hanging off the side. With an organic acid, you can identify organic acids in the condensed formula with COOH, COO. And then your product is always going to be a ester. What's an interesting characteristic of esters? Anyone remember an interesting characteristic of esters? Good. They have scents. They're smelly. So esters can have very fragrant smells. And then your other product is always going to be water. Okay, so this one popped up a little early. So this was our next one. You guys all said that it was addition reaction because we're going to add the chlorines into the compound. To do that, we have to break the double bond. So you're always going to start with an alkene and a halide, and they're going to add them together and be addition reaction. And this last one looks similar to the addition reaction, but it is a little bit different. This is a substitution. Very good. So you're basically going to substitute it. For this one, I tell my students, remember, like, what is a substitute teacher? For example, they take the place of the teacher for the day. So that's pretty much what's happening here. One of these chlorines is subbing in for one of the hydrogens. So we're creating a new HCl so that one of the hydrogens in the methane is being kicked out and chlorine is taking its spot. And then the other chlorine is combining with that hydrogen. Very good. There's two other ones. Saponification is another one that you want to know. The key word you want to watch out for here is soap. So saponification, you're always going to be reacting some type of fatty acid with a base. So NaOH is a base. Why isn't that an alcohol? It has the OH. We were just saying OH is an alcohol. Okay, so this is not an alcohol. Is not an alcohol because it is not an organic compound. So we have a metal with the OH making it a base. And then in saponification, your two products are always going to be an alcohol and a soap. Usually they'll write the word soap. The last one is polymerization. Poly means many, so we're going to be taking out many small chains and combining them to make one very long chain. So those are the major types of organic reactions. Like I said, if this was tough for you, there is another, I think it is the last review session today from 7 to 8 tonight. That's on organic chemistry, so you might want to tune into that one. Okay, another classification of reactions would be nuclear reactions. Take a minute, ponder the difference between these two nuclear reactions. Okay, so the major difference between these two reactions is this one. We're starting with a rather large element, uranium-235, and we're going to hit it with a neutron in order to start this reaction. And we're going to break it into two medium-sized nuclei and 3 neutrons. And what are these 3 neutrons going to go on to do? Well, they're going to cause somewhat of a chain reaction. They're going to go on to hit more uranium atoms and then continue the reaction. This is going to produce a lot of energy. And if you correctly identified this as fission, you are correct. If you remember from bio, if you've already taken bio, fission reactions, like binary fission, we've heard this word before, is when an organism divides itself into 2 equal pieces. It's pretty much what's happening here. You end up with 2 medium-sized nuclides from 1 large one. And then you have the neutrons in there as well. The next one is a fusion reaction. And if you think about what the word fuse means, it means to put together and make larger, to fuse them together. So we're taking 2 hydrogen isotopes and we're going to fuse them together to make a helium atom, a neutron, and lots of energy. This reaction actually is going to produce more energy than the fission reactions. This one gets done in the sun. There is the hydrogen bomb that does the fusion reactions. Both of them produce a lot of energy compared to any of the chemical reactions. So one of the benefits of using any of these would be just more energy produced. Okay. Okay, let's ponder this one for a minute. It says a student adds 1 molar NaOH with 2 molar HBr. Complete the following reaction. Very common part 2 question. Okay, so If you're looking at this type of reaction, we have, what type of reaction would this be considered? So I included it with the types of reactions. I see some of you already answered it, which is good. What type of reaction would this be? This is neutralization. Great job, guys. And the products of this would be NABR and H2O. Now, when you're writing, if you realize that it's a neutralization reactions are going to have a base. So you're going to have a metal with the hydroxide ion, and then an acid. So you're going to have hydrogen with a negative ion. And when you add them together, your two products are always salt and water. Now, be careful. Salt is not only NaCl. I know a lot of my students make this mistake, so I don't want any of you to do that. A salt is anything that is ionic. So when we're looking at this, what I say to do, cross out the hydrogen, cross out the OH, doesn't matter how many of them there are, and then whatever's left becomes your salt. So in this case, if we take out the OH and the H, what's left is our Na and our Br. So that becomes our salt, our ionic compound, and then the other product is water. Okay, so this is going to work for any anytime you react an acid with a base. So I know a couple of you are confused. So let's try another one. Let me exit out of there for a second. Okay. So let's say we had MgOH2, and it reacts with, well, this should be working. Technical difficulty, just stick with me for one moment. Oh, there it goes. Okay, so let's say we have MgOH2 and it's reacting with, let's say it's HCl. Okay, so when you're looking at it and you're trying to figure out what is going to happen and you're trying to predict the products of this, it's neutralization because we have a base. A base is going to be a metal with the OH and an acid. So anytime you mix an acid and base, you're neutralizing them. One has a very low pH, one has a very high pH, and you're going to bring it closer to 7, which we know is neutral. Now, if we're trying to predict the reaction, the products of this reaction, we get rid of the OH, we get rid of the H. That's going to become H2O. So one of our products is going to be H2O. And then the other product is going to be whatever is left off. So in this case, it would be Mg and Cl. Now, since this is ionic, we have to be careful with our ionic formula writing. We have to look up our oxidation numbers and then make sure that the compound is neutral. So magnesium is a +2 oxidation number, chlorine is a -1 oxidation number, which means we're going to need 2 chlorines for every Mg. So it's going to end up being that. So that's going to be your product of this reaction. You're going to have the water and then this ionic compound, which we call a salt. So don't be confused with salt being ionic. Don't automatically jump and think that it's going to be NaCl. That's a common issue with that. Okay, so back to this. Oh no, just kidding. We were up to all right, moving on. Last type of reaction I want to go over really quick. You're going to have a whole thing on redox later, but it is a type of reaction you want to be able to recognize, especially. So how would you determine which one of these is a redox reaction? To do that, you would look and see if oxidation numbers are changing. So if we look at this, We have 4 options here, so I'll give you a moment just to look at them and see if you can figure out which one of these is going to be the redox reaction. Just want to thank a lot of you for helping out each other. This is great. I see a lot of good conversation going in the comments section. So thanks for helping out explain things. There's a little bit of a lag between my video and your comments. So continue to help each other. It's great. Great job. Everyone seems to be getting this one right. The first one is a redox reaction. So if you're not sure, a trick is that single replacement reactions are always redox. So if you look through and you see a single replacement reaction, that is automatically a redox reaction. But all of the other types, you're going to have to assign oxidation numbers. Double replacement are not usually redox reactions, so those typically aren't going to be your choices. But decomposition and synthesis could be. So if we look at this, Mg is going to have a 0 oxidation number because it's an atom by itself. Chlorine, even though there's 2 of them, it's diatomic element. So this is always also going to have a 0 oxidation number. And then their oxidation numbers are going to change to Mg plus 2 and Cl minus 1. So the reason that this is classified as a redox reaction is because your oxidation numbers are changing. You have something that's going to be oxidized and another one that is going to be reduced. So great job. If you went through and assigned your oxidation numbers for all of these, I wouldn't recommend it. But if you did, you would see that none of the other reactions are going to have changing oxidation numbers from one side of the reaction to the other. All right, so if you need to get up, stretch a little bit. I know that we've been working at this for a while now. We're going to head a little bit more into balancing reactions and stoic for the second half of this. I hope if anyone has any questions too, let me know. I do have the comments running, and like I said, there is a little bit of a lag, so if it takes me a minute to respond to you, I apologize. All right, we all ready to keep going? Okay, next one, everyone's favorite thing to do, balancing reactions. You want to remember a couple key things when you're balancing reactions, though. You want to remember that your coefficients are going to represent your mole ratios in the reaction, meaning that the number before the compound in a balanced reaction tells you how many moles of that is going to react in that reaction. You need to make sure that you have equal number of each element on both sides of the equation, and we're trying to abide the law of conservation of mass there. You want to balance using the smallest whole number coefficients, meaning there are going to be, when you balance it, you might end up with higher numbers. You want to always check before you write down your final answer that you have reduced it as much as you possibly can. So sometimes it's easier to figure them out a little with higher numbers, but then just make sure at the end you end up with the smallest numbers possible. So if everything's divisible by 2, make sure you divide it by 2. And then remember, balanced equations always fulfill the law of conservation of mass, energy, and charge. So charge we do a lot with the balancing redox reactions. Law of conservation of mass we've been doing with balancing actual reactions. Okay, so this is where you might want a piece of paper out just so that you can balance with us. If you could do it in your head, that's great. All right, so try this one. So Fe plus O2 gives Fe2O3. So I want you to balance it using the smallest whole number coefficients. Okay, so I see a few of you got the right answer. So if you look at it quickly, you would see that we have, what I would recommend doing is making a little list of what you have on each side of the equation. So we're starting with 1 iron on this side and 2 oxygens on this side. On this side, we're starting with 2 irons and 3 oxygens. What you might want to do initially is you're going to want to jump to this iron and balance that first. So you put a 2 here. But the bigger problem is going to be that we have 3 oxygens here and 2 oxygens there. So I always pick the harder one to start with. So because those two numbers are not the same, and we can't multiply this by anything to get 3, then we're not going to, that's going to be a little bit tougher. So find a common multiple between 2 and 3, which would be 6. So we're going to multiply this one by 2. By doing that, we're going to have to update our iron count later. So I always save the one that's by itself for the end. So when you correctly balance this, you should end up with 4, 3, and 2. I see a lot of you got that, which is great. So you just want to make sure that at the end, you go back and you check. This is one of the only real times on this Regents that you can be 100% certain you got that right, because you should be able to count the elements on both sides and make sure that you have the same number. So if we look here, remember our coefficients are going to get distributed to both of our elements. So we have 4 irons and we have 6 oxygens. So we multiply the 2 and the 2 and the 2 and the 3. So we have 4 irons, 6 oxygens on this side. We have 4 irons and 6 oxygens on that side. So you know that you balanced it correctly. All right, let's try another one. A little more complicated, not much harder. Okay, I want to remind you too that the comments are supposed to be like chem-based, and you should be using it to help each other review this material. If you don't want to participate, that's fine, but please do not leave any insulting comments to anyone. Okay, so looking at this, equation, we're going to do the same thing. You're going to make a list of what you have on each side of the equation. So you're going to have, we start with 1 nitrogen on this side, 1 nitrogen on that side. Okay, right now that's balanced. We have 4 hydrogens over here, but we have 5 hydrogens over here, so that's going to be a little bit more of an issue. We have 1 chlorine here, 2 chlorines there, so we know that we're going to have to do something with this compound. 1 calcium, 1 calcium, and 1 oxygen, 1 oxygen. So when you go through and you make your list and you start comparing how we're going to get there, if you come up with so we can pick one thing to start with. So it doesn't really matter where you start on this one. So we start with 1 nitrogen, 4 hydrogens, 1 chlorine, 1 calcium, 1 oxygen on one side. We have on the other side, we have 1 nitrogen, 5 hydrogens. Remember to combine these two here to make 5. You have 1 oxygen, you have 1 calcium, and you have 2 chlorines. So start with the things that aren't balanced first. So we see that this is an odd number of hydrogens, so eventually we're going to have to get to an even number. So what I would recommend is trying to get that to an even number first. So if we put a 2 here in front of the nitrogen and update our counts, we end up with 6 hydrogens now, 8 hydrogens. And then we also have 2 nitrogens, so we can put a 2 in front over here. So you would end up with a 2 here, yeah, you would have a 2 in front here and a 2 in front here, and then the rest of it would be balanced. So it looks really complicated when you're first looking at it, but not really a hard balancing equation. So the coefficients would be 2, 1, 2, 1, 1. Okay, so this question came up in a practice session I did with my students not too long ago, so I wanted to throw it out there. It's a 3-part question, so take a moment. Let's work on question 51 first. It says, so they're giving us a balanced equation here. They've already balanced it for us. It says, determine the mass of CO2 produced when 9 grams of glucose completely reacts with 9.6 grams of oxygen to produce 5.4 grams of water. Okay, so when we look at this, it looks like we might have to do some conversions to moles. I know a lot of my students tried to convert all of these to moles and then run mole conversions, but it's actually a much easier question than that. If we follow the law of conservation of mass, we know that the mass of our reactants should equal our mass of our products. So if we look at that and we go from that way, we know that we have 9 grams of glucose, we have 9.6 grams of oxygen. So this side of the equation comes to 18.6 grams. We know that this side of the equation should also be 18.6 grams. So we know that the water is 5.4 grams. So all we have to do in that equation is subtract them, and you should get to 13.2. So great job for those of you who are following along and got 13.2. I know a couple of you said that. So for this question, you didn't have to do any conversions. You just had to remember that the mass on one side of the equation should equal the mass on the other side. So they were, in my opinion, trying to trick you a little bit into trying to think it's a much more difficult question. This kind of question has shown up many times on the Regents. So just remember your basic rules and you'll be fine. Okay, the next one said compare the entropy of the reactants to the entropy of the product. So remember, entropy is randomness. So we're looking at randomness. We have a solid over here and we have a liquid over here, and these two are gases. So what happens to the randomness in this equation? Well, the entropy of the products is greater than the entropy of the reactants. And then the last one was the empirical formula of glucose. Kind of a random question in here, but remember our molecular formula shows us exactly how many of each element we have. The empirical formula is going to be the reduced version of that. So if you reduce C6H12O6, a lot of you are following along and got this one, is CH2O. Great job. Okay, so going on to stoic and the mole for our last little bit. This is not difficult calculations, but it's one that you want to practice a little bit. So remember, we can use balanced equations to figure out mole ratios. It has to be balanced first. So if you come across a mole ratio question, you have to make sure that they gave you a balanced equation. If they didn't, you have to balance it before you can begin. Okay, so first, let's try this easy conversion. Remember, you have a mole calculation equation on the back of your reference table. So if we look on the back of the reference table, we have a mole calculation. It says how many moles is contained in 3.8 grams of NH4Cl. So take a moment to answer that. I'm not sure that you guys are seeing what I want you to see. Okay, so for this one, you want to set it up with 3.8 grams over the gram formula mass of NH4Cl. Remember, for the NH4Cl, you just have to look up the masses on the periodic table and add them together. I always recommend you round to the 10th. Just be careful on that rounding. So we get the 3.8 from the equation. Then the given mass is what they give us. And then we just have to divide them. And when you divide them, you come out to... should come out to 0.07 moles. So I know a bunch of you put that, so that's great. And then you just divide the two. Okay, here's another one. This is a mole ratio question. So on this one, they're giving us the balanced equation already, and it wants to know the mole ratio of NaOH to AlOH3. So give me a second, think about it. Good job. A lot of you put the answer as 3. So when we're looking at the balanced equation, you first want to look at the moles that they're giving you as the coefficient. So NaOH is 6 moles and Al2OH or AlOH3 is 2 moles. So at first glance, this should be a 6:2 ratio, but you can reduce that to a 3:1 ratio. So you always want to reduce those ratios. So 3 was the correct answer. Great job. Okay, try this next one. The coefficients in a balanced chemical reaction represent. Okay, so I'm seeing a little bit of disagreement, a little bit maybe. Okay, so the correct answer is 2. So the mole ratios of the substance. We always call these the coefficients, but remember they do represent the moles in the equation. So we're able to figure out the mole ratio based on the balanced equation. Remember, you first need to balance before you can do any of this. Great job. All right, let's try this one. So given the following reaction, I want you to do 2 things. First, I want you to balance the equation using the smallest whole number coefficients, and then I want you to figure out how many moles of CuSO4 are consumed in the production of 2 moles of Al2SO4(3). Okay, so if we're looking at this first one, first you had to balance it. So if we're looking at the balanced equation, if you balanced it with us, then you should have the coefficients 2, 3, and 3 over here. So we have 2 aluminums on this side of the equation, 2 aluminums on this side of the equation, 3 Cus on this side, 3 Cus on this side. And then what I wanted to point out, if you have a polyatomic on both sides of the equation, so we have SO4 here and we have SO4 here, don't actually have to break it up into the S and the O's and count them separately. You can treat it as a polyatomic. So we have 1 SO4 on this side, we have 3 SO4s on this side, but because of the 3 in front, we're having 3 and 3. So hopefully everyone was able to balance that out correctly. It looks like most of the responses coming in are correct. Okay, the next part is a little trickier. It says how many moles of CuSO4 are consumed in the production of 2 moles of Al2SO4(3). So take a moment to answer that one, and then I'll go through how I would answer it. Okay, so now if we're looking at this equation, it says how many moles of CuSO4 are consumed in the production of 2 moles of Al2SO4(3). So we have moles of something to moles of something else. So that's what we're not converting a mass to moles, so we can't use the equation on the back of the reference table, but we can look at our mole ratios. We know that 3 moles of this is used in the production of 1 mole of this, so we can set up a proportion. So we can go 3 over X, because we don't know how many we're going to need, equals 1, our number from our balanced equation, over how many are in the question, which is 2. So our proportion would be 3 over X equals 1 over 2. The top numbers came from our balanced equation. Our bottom numbers came from what was in the question, so X and 2. And then when you solve that, you should get X is equal to 6, so 6 moles. Great job for those of you following along. So our last two questions came from the studio audience. They were submitted over the course of the last few weeks. So this is the first one. It says, how many moles of Al react completely with 4.5 moles of O2 to produce 3 moles of Al2O3? Well, when I first got this question, I was like, well, how do you do that? But then I realized that you need the equation before you can actually do this. So here's the equation. What's the first step when you're doing something like this? First step is always going to be to make sure that you have a balanced equation first. So go ahead and balance this equation. Okay, so the balanced equation is going to look like this. So you do want to make sure that you balance it correctly first, because if you don't do that part of the question right, then the next part is going to be difficult. So now it says, how many moles of Al react completely with 4.5 moles of O2 to produce 3 moles of Al2O3? So we're trying to figure out how many moles of this are going to react to produce 3 moles of this one. So to do that, we're going to read through the question. We're going to put our question information underneath our balanced equation. So it says how many moles of Al. So I'm going to put X right under there. If you do it this way, it's going to set up your proportions for you. So I know a few of you said that you had your proportions wrong before. But if you kind of go through step by step, then you'll be fine. So it says how many moles of Al2 will react? Well, we don't know that. So we're going to put X under the Al. With 4.5 moles of O2 to produce 3 moles of Al2O3. Okay, so we put the 3 moles of Al2O3 underneath, and it doesn't, in this question, it's not going to matter which one of these two you use. So if you set up your proportion using this one, or if you set up your proportion using this one, it doesn't actually matter. So I'm just going to do it with these two to make the proportion easier. So our proportion becomes 4 over X equals 2 over 3. So that's set up for you, and then all you have to do is cross multiply, and you should get 6. So you do 4 times 3 equals 2x, which is 12 equals 2x, and then you divide by 2, and you end up with 6 moles. So great job. A bunch of you set it up correctly, which is wonderful, and then a bunch of you got it right. Great job. Okay, our last question. So it says, given the balanced equation representing the reaction. So we have a complicated one, but luckily they're balancing it for us, so we know that at least that part is correct. It says, what is the mole ratio of NaOH to AlOH3? So you can do it the same way. It says, what is the mole ratio? So we want to find NaOH, that's here. We want to find AlOH, which is here. So I want you to determine the mole ratio. Okay, so initially it's going to look like a 6:2 ratio, but remember we can reduce those mole ratios to a 3:1 ratio. So we end up with a 3:1. Very nice job, everyone. Okay, so thanks for hanging out with me this morning. I know it was early, but you guys did a great job helping each other, especially. Continue that throughout the day. Because it's difficult for us to comment back while we're doing this as well. But you guys were helping each other, and I really think that's going to help you on the Regents. Best of luck on the Regents next week. Remember, the next session starts at 9, and they go through all day, and you can go back and watch them. So if you have something to do today and you can't tune into all of them, go back later. You can watch them throughout the week. Good luck. See you soon.